Okay, so let's now carry out the calculation of the length of the curve C. As you see, I don't have the picture of the sphere anymore, but all the calculations and notation refer to the previous video. So if you recall, in the previous video we had a sphere and 2 points, P and Q. The point P was the North Pole, and the point Q was somewhere on the XZ plane. And then we connected these 2 points by a curve C. And we wanted to calculate the length of that curve C, and we wanted to show that the length of that curve is greater than or equal than phi0. Phi0 was the length of the arc of the great circle that connected the points P and Q. So if we show that the length of that curve is greater than or equal than phi0, that means that the arc of the great circle was the shortest possible curve joining P and Q. All right. To do this, this was the formula, of course, for the length of any curve in R3, so in particular the curve C. And to make the calculation doable, I will carry this out in spherical coordinates. So if you recall the spherical coordinates, in spherical coordinates, the coordinate x is equal to cosine theta sine phi, y is equal to sine theta sine phi, and z is equal to cosine phi. Phi is the angle between the point on the sphere and the z-axis, so that in the previous video was my second spherical coordinate, while the first spherical coordinate theta is whatever you get when you project that ray joining the origin and the point on the sphere down onto the xy plane. So you'll get a ray in the xy plane and forms a certain angle with the x-axis, and that's theta. Okay, the only thing I really need to know now about theta and phi is that in my parametrization of the curve C, the parameter was little t, and it changes between two values, 0 and capital T. When the little t is equal to 0, I'm at the point P, so I'm at the North Pole, which means both of the polar coordinates are 0. Phi of 0 is 0, and theta of 0 is also 0. When at the end of the curve, when the little t is equal to capital T, I'm at point Q, and at point Q, the value of phi is equal to phi0, and on the other hand, theta is still 0 because point Q, by our choice, still lies in the xz plane. So the original and the final value of theta is 0. However, in between, this curve C can stray away from the great circle that lies in the xz plane, so theta might be non-zero. Okay, so to carry out this computation with these coordinates, I need these derivatives. All right, and that's just simple calculus. That's essentially a combination of chain rule and product rule here. So I have a product of two functions, cosine and sine. So the derivative of the first function, that's going to be negative sine. See, I'm dropping the dependence on t from all these to just make these formulas a little bit more transparent. So of course all the thetas and phis still depend on t. So derivative of cosine theta is negative sine theta times the derivative of the inner function, so d theta over dt, times sine of phi, plus the first function, unchanged, times the derivative of the second function, which should have been here cosine. Even if you do calculations beforehand, you make mistake. I make mistake. Okay, so that's the derivative of sine is cosine, so that's cosine theta cosine phi d phi over dt. Okay, we do now the same thing with the y function, so let's check that this is now correct. Derivative of sine is cosine times the inner function times sine of phi plus sine of theta, derivative, also derivative of sine phi is cosine phi times d phi over dt. And finally, when z of t is equal to cosine phi, the derivative is minus sine phi d phi over dt. The next thing that I need to do is to square all of those. So let's square x prime of t first. So look, x prime consists of these two terms, this and that. So think about it as a plus b. So when I square a plus b, I get a squared plus b squared plus 2ab. So a squared, that's sine squared of theta, sine squared of phi d theta over dt squared. I'm putting the derivative at the end. Plus, now here I have to correct that mistake. So that's cosine squared theta, cosine squared phi, d phi over dt, minus 2 sine theta sine phi cosine theta cosine phi d theta over dt times d phi over dt. Okay, let's square y prime. That's cosine squared theta sine squared phi d theta over dt squared plus sine squared theta, and this is now going to be cosine squared phi d phi over dt squared plus 2 cosine sine phi sine theta cosine phi d theta over dt times d phi over dt. And finally z prime, well, that's easy to square. That's sine squared phi d phi over dt squared. Okay, what I need to do, right, is to add all these. So I'm putting plus signs in between them and see what I get. So this sum here, maybe I'll just write it on the top, leaving that up but erasing that. So x prime of t squared plus y prime of t squared plus z prime of t squared is what? Well, first of all, let's look at these two terms. Sine theta, sine theta, sine phi, cosine theta, cosine theta, cosine phi, and the same derivatives, but opposite signs. So these two terms just cancel out. Let's look at these two terms now. What do I have here? Well, both of these terms have a common factor, namely cosine squared phi d phi over dt. So I can factor out that cosine squared phi d phi over dt, and what I will have left inside the parentheses would be sine squared theta plus cosine squared theta. But sine squared plus cosine squared of the same angle is 1. So this thing gives me cosine squared phi d phi over dt squared times 1. So that's all I get from here. Then, if I look at these here, I have a similar situation, right? I can factor out sine squared phi times d theta over dt squared. So what I will have left is sine squared theta plus cosine squared theta, and that's 1. So that also gives me just sine squared phi d theta over dt squared. Okay, so what do I now need to add? I need to add, what do I have left? I have this, this, and this. These are the three pieces that I need to add. But look again. Look what happens when you add these two here at the bottom. You can factor out d phi over dt squared, and what you will have left is sine squared phi plus cosine squared phi, and that's again 1. So these two terms together just give me d phi over dt squared. Because that's d phi over dt squared times 1, right? D phi over dt squared times, in parentheses, sine squared phi plus cosine squared phi. So altogether, I get that this is just sine squared phi d theta over dt squared plus d phi over dt squared. Okay, so once we have that, we can forget about this nightmarish calculation, and we have a rather uncomplicated formula. So this integral, so the length of c is equal to the integral from 0 to t, square root of that expression. Okay, well, that is some integral. If you just forget about the phi and the theta here, they are just functions of t, right? Everything here is a function of t, so it's a function of one variable. If I wanted to, I could just graph it somewhere as a graph of a function of one variable. So here will be t, and here will be that function, whatever that is. It's like, I don't know, function. And we start from 0, and we end with t. And look at what kind of function this actually is, right? This thing here is positive, or non-negative at least, right? And so is this. And in fact, the radical of it is also positive. So, and that's like at every value of t, these things are positive. So that means the graph of that whole radical is just something that lies above the t-axis. And the integral is just the area of this. But think about what would happen if I just forgot about this and I just looked at that. Well, that is also a positive function, but the graph of just the square root of that bit lies below that purple graph over there, right? Because if I just do this, that's less than that. So the graph, which I'm just going to mark in green here, is somewhere below. That's the graph of the square root of d theta dt squared. And the purple graph is the graph of the whole thing, right? So this green graph certainly lies below the graph of this whole thing because the whole thing has this extra positive term here. That means I can say that this integral is certainly greater than or equal than the integral from 0 to t of just the square root of d phi over dt squared. Okay, well, but that one is actually easy to do. That's the integral from 0 to t of the absolute value of d phi over dt dt. And furthermore, the absolute value of any real number is always greater than or equal than that real number. So this is greater than or equal than the integral from 0 to t of just d phi over dt dt. And this is like the derivative of phi prime, right, times dt. So I can do a change of variable here. And my new my current variable is little t, but I can make my new variable to be phi. And then the change of variable formula from calculus just gives me d phi here. But I have to recalculate the bounds. So when little t is 0, then what's phi? Oh, phi is also 0. And when little t is capital T, then what's phi? Oh, phi of t is then, it's phi 0. So I get that integral. That's just change of variable. In other words, substitution. Oh, but this is now very easy integral. That's phi. So that's phi 0 minus 0. So phi 0. So if you look throughout this sequence of inequalities, what you get is that L of C is greater than or equal than phi 0, which is what we wanted to show, right? So in other words, what that shows is that the length of that curve C, and the curve C was completely arbitrary smooth curve on the sphere joining P and Q, the length of that curve is at least phi 0. It's greater than or equal than phi 0. And phi 0 was the length of the arc of the great circle joining P and Q. So that arc of the great circle is the shortest possible curve you can get between these 2 points.